Hi, I'm Dr. Bruce DiNardo here in the physics department of the Naval Postgraduate School in Monterey, California. In another video, we demonstrated the fundamental magnetic force on a charged particle that is moving in a magnetic field. In this video, we will explain and demonstrate the magnetic force on a wire that is carrying an electric current. Surprisingly, the reverse demonstration can be done, which we will also explain and do. Suppose that we have a current-carrying wire in a magnetic field. We know that there are magnetic forces on the moving charges. Because these charges are confined to the wire, there will be a force on the wire. For a straight wire that is perpendicular to a uniform or spatially constant magnetic field, the fundamental magnetic force law tells us that the force is perpendicular to the field and the wire, with the direction given by the right-hand rule. The magnitude of the force is the product of the current, the length of the wire, and the magnetic field. Here is a demonstration of this effect. A segment of wire passes between the pole faces of a magnet. The magnetic field points from the North Pole to the South Pole. Positive current will flow from the red to the black terminal. So the current will flow down here and along there. The current is here. The magnetic field is there. The force, by the right-hand rule, should be directly outward. Let's do the demonstration. I will turn on the current from the power supply, which will cause roughly 5 amps to flow through the circuit. You can see that there is a force that is indeed outward. If the current is reversed, the force should be reversed. I'm going to switch the leads here and now turn on the current, and you can see that the force is reversed, as it should be. Let's go back to where the force is in the outward direction. Force is in the outward direction. And now let's flip the magnetic field. That should also cause the force to flip. I turn on the current, and it does indeed flip the force. This is all just what the magnetic force law predicts. Many physical phenomena are reversible. The technical name is reciprocal. Is the jumping wire demonstration reversible? That is, instead of putting a current through the wire to cause it to move in a magnetic field, what if we move the wire in the magnetic field? Will a current be generated? We consider the case where the wire is moving perpendicular to the magnetic field. There are moving charges in the wire, but they now experience a magnetic force that is along the wire. This generates a voltage across the wire. If the circuit is closed, there will be a current. The jumping wire demonstration should thus be reversible. Can we demonstrate this? Note that the wire forms a pendulum here. If we start the pendulum oscillating, the wire moves back and forth in the magnetic field. So we just have to connect the wire leads to an oscilloscope and look for a voltage. I'm now going to move the pendulum. You can see that it appears that there may be a signal there, but there's way too much noise. Part of this is due to the wire leads acting as an antenna loop that picks up electromagnetic noise. If the leads are twisted together, we get a significant reduction of the noise, as you can see. Now let me start the pendulum. There's clearly a signal there, but there's still a lot of noise. To further reduce the noise, we use a preamplifier that has built-in filters. I have set the filters to remove most of the noise below and above the pendulum frequency. I have also set the gain to 1000. In the end, you can see that we have greatly increased the signal-to-noise ratio. When the amplitude of the pendulum is large, note that a significant voltage occurs only when the bottom wire is in the magnetic field. As the amplitude of the pendulum decreases due to damping, and I have to increase the gain of the oscilloscope, note that the bottom wire spends more and more time in the magnetic field. The signal becomes more and more sinusoidal, which it should. Putting an electric current through a wire in a magnetic field can cause the wire to move. This is the well-known jumping wire demonstration. The force is due to the fundamental magnetic force on the moving charges. The result is that we have a motor, which is any device that converts electrical energy into mechanical energy. Remarkably, the reverse process can also occur. Moving a wire in a magnetic field can cause a voltage to occur across the wire. This voltage can then be used to produce an electrical current. The result is that we have a generator, which is any device that converts mechanical energy into electrical energy. Simple physics demonstrations such as these fundamentally contributed to the Industrial Revolution. Physics lecture demonstrations are always fascinating, and the quest for them never ends. This is the Physics Department of the Naval Postgraduate School, and I'm Dr. Bruce DiNardo. Thank you.